Welcome to episode 5 of the Haskell Cast. I'm Rain Henricks with my co-host Chris Forno. Our guest today is Brent Yorgey. Brent is the author of the Typeclassopedia and the creator of the Diagrams Library. He's also been an editor of the Monad Reader and the Haskell Weekly News. He is a PhD student at the University of Pennsylvania, where he also teaches an Introduction to Haskell class. Did I miss anything, Brent? Is that good?
Not to know of, yeah.
Awesome. Well, welcome to the Haskell Cast. We're really happy to have you here.
Thanks, I'm glad to be here.
I thought we'd start out maybe by talking about what Chris likes to call your road to Haskell.
Okay.
How did you discover Haskell? What was it like learning it? How did you decide to make it such a big part of your career?
Right, yeah, that's a very interesting question. So, I think the first time I ever saw Haskell, I was in high school. This would have been, like in the late 90s. And so Haskell was, not too old at that point. And I remember downloading Hugs and playing around, in the interpreter. But I never got very far, and I don't even think, I don't know even how much material was out there. It was just something fun I was playing around with and then put aside. And it wasn't until, I think it was in 2006 that I first sort of got into Haskell seriously. And I had seen a little bit of functional programming in a PL survey course in undergrad, that kind of thing. Did some Lisp for an AI class, so I had a little bit of experience with functional programming. But it was 2006, I think it was. My wife was doing a month-long study abroad program, so I was sitting at home with no one around and a boring job. And I think I saw some blog post saying, "Oh, there's this Haskell language that's pretty cool." And I said, "Well, it's interesting. Let me check that out." And and it kind of snowballed from there. I mean, I think if you made a movie of it, it would be one of those things where you sort of have a cut shot from that moment to me sitting at a desk surrounded by piles of papers printed out that I had been reading and scratching my head over some complicated code.
Could there be one of those Rocky-style training montages?
Yeah, no, it would definitely be one of those, yeah. But it was funny because, in undergrad I had kind of ruled out programming languages. I had decided that it wasn't really something I was that interested in. I thought maybe I wanted to do grad school, but I wasn't sure exactly in what subject. But then, this was two years out of undergrad that I started learning Haskell and ended up, started learning the language and then ended up reading all these academic papers. And at some point I had this realization. I said, wait a minute, this is programming languages. Why didn't anyone tell me it was this cool? I don't know, maybe people tried to, but for whatever reason it didn't stick before. But I don't know, the process for me, I think because I had had some exposure before a few times, and it was just something that seemed fun, I was really motivated, and I had a lot of time. The process for me was pretty smooth and sort of learning it. I don't know if I know some people, if they come to it cold, they kind of have difficulties or have to start several times, but
Did you start out with more of a mathematical background?
Yeah, I mean, I've always really loved math, and in undergrad, I was a computer science major. I technically was not a double major with math, but during my senior year, I think there were some of the math professors that were surprised to find out that I was not actually a math major. I just took all the math classes that I wanted. So I definitely had a strong math background already at that point, and I think that probably helped a lot too, just in picking up the abstractions. But and certainly, I'm sure we'll talk more about this later. But that's a big part of sort of my identity as a Haskell programmer, that I'm always looking for elegant mathematical abstractions that are underlying whatever I'm working on. And I think that's one of the things that I love about the community or the culture surrounding Haskell. It's not just me that does that. So.
Yeah, one of the things that really got me into the mathematics, the algebra and the category theory, and how it relates to Haskell was your monoids Perl.
Mm-hmm.
Reading that about how diagrams form a monoid and how you can join them together in that way is what sort of put the spark that it isn't really just abstract nonsense.
Right.
There are actual practical applications. So how do you approach tying Haskell to the abstractions that math provides? Do you have a problem statement in Haskell, and then you start looking through math to find good solutions?
Yeah, that's a good question, and I think that the Monoids Perl paper that you referenced is a good example of that. I think the content of that paper, really was several years in the making, and it's a very nonlinear sort of process. I wish it was nice and simple, where you just say, okay, I'm going to write down my problem statement, and then I'm going to find some math that fits, and then I'm done.
Yeah.
But it really doesn't work that way, and it's really more an issue of, writing something, trying to get it to work, and along the way, sort of always trying to think about what is the sort of abstract essence of what I'm doing, and kind of iterating on that, and you discover, you make some discovery, and you are able to structure your code in a different way, and it becomes a little more elegant. But then that leads to other problems, and then you realize that this abstraction doesn't quite capture everything, and so you need to go back to the drawing board. So it's knowing a lot of abstractions certainly helps, because you need to be able to recognize patterns. But sometimes I've come to mathematical abstractions from the other direction. So, for example, in my diagrams library, we now make a distinction at the type level between vectors and points, which is something that a lot of people that just sort of sit down and write down some code for doing computational graphic stuff kind of say, well, a point or vector, it's the same thing. It's just a pair of coordinates. But it turns out that these things form what's called an affine space, and I had never heard of an affine space, and I did this. The first version of diagrams did this, conflated them, and ran into some bugs, and realized that this isn't right. These are different, and then kind of through that found out about affine spaces and was able to structure the code that way. So.
And it seems like there's also there's a linear library that Edward Comet wrote, which is sort of the opposite approach, which is here are all the mathematical concepts, let's reify them as Haskell libraries, which is just what he does all over the place.
Yeah. Yeah, indeed. Yeah, linear is really nice. So diagrams actually uses Connell Elliott's vector space package.
Mm-hmm.
I think we could probably use linear instead. At this point, it would be a lot of work to switch, and I don't, I think both would serve our purpose as well.
Yeah, so let's talk a little bit about diagrams, especially since I saw that you released version 1.0 pretty recently.
That's right. Yep.
So what exactly does it give someone, and maybe you can explain kind of at a high level what it improves on as far as maybe TikZ or somebody else who's been using some sort of programming graphics system.
Right. So there's sort of two, well, there's a lot of things, but so in comparison to TikZ, one of the biggest benefits is that diagrams is embedded in Haskell, and TikZ is embedded in LaTeX. And LaTeX as a programming language is not very nice for doing anything other than typesetting documents. So if you need to compute anything, or if you want to take some data and visualize the data, or you want to write a program to get some data from somewhere and then make a picture out of it, doing that in TikZ is going to be a real pain in the butt. And what people end up doing is they write another program in some other language that outputs TikZ, or outputs something that TikZ can read in and make a diagram. And it's just extra extra layers and places where you can mess things up. So the fact that diagrams is embedded in this powerful language, Haskell, which has a huge ecosystem of other stuff that you can integrate it with, is really nice.
And is also Turing complete, unless text became Turing complete at some point that I don't remember.
Oh, I'm sure it is. Oh, no, absolutely it is.
Oh yeah, that's
but,
right.
Yeah,
Probably a little bit less expressive.
Yeah, but I don't know.
I think
not sure which
the
I'd rather
problem
program
with the problem with tech is you're dealing with something with a lot of, I don't know, you can call it macro substitution or
Yeah.
Yeah, so
Yeah, exactly.
so it's basically a way to create pictures, diagrams, images, graphs, whatever you want to call it, in a programming language, and maybe you can explain your motivation for writing it. You were working on your blog, I believe.
Yeah, so this was I don't even remember the details, but this was many years ago. So I have two blogs. I have one that's sort of about Haskell and academic stuff, and another that's um, sort of explaining cool, beautiful math. Sort of, it was originally aimed at a high school audience, but I started it when I was teaching high school math. But it's really for anyone. But I think it was on that blog. I was writing some blog post, and I wanted to illustrate something with a picture, and I knew exactly the picture that I wanted, but it was going to be really tedious to draw it in Inkscape or whatever. And I said, well, okay, surely there has to be some kind of software out there that will let me, generate a picture like this. And I looked around, and certainly there is software that lets you generate pictures, but none of it looked like, what I thought it should look like. And so with typical programmer hubris, I said, well, how hard can this be? So, I hacked something up in 2 weeks, and it made some pictures. I'm pretty sure it could not make the picture that I wanted it to make in the first place. And then I spent about a year sort of thinking about it and redesigning it, and then sort of rewrote it from scratch, and have been working on that one since. So that was the genesis of it, and I still use it a lot. I mean, for illustrating things on my blog, in papers that I write. So it's really been successful in that sense, just in scratching my own personal itches.
So tying that back to tech, I saw that it has at least some of the functionality of metafont in it as well. How much of a process was that to implement, and how complete is the implementation?
Oh, so it's only one small piece of metafont, which is a very cool piece. But so what it does, metafont has this syntax for describing paths, where you can not just say, I want the path to pass through these points, but when it passes through this point, I want the tangent line to have this slope, and I want the line between these points to be sort of curvier or less curvy. There's various sort of parameters you can control, and then it solves a big system of linear equations and generates a nice spline that fits all your parameters. So we have that now. So and actually I started the implementation. I thought this would be cool, and I got about halfway and sort of got really confused and gave up and put it aside. And then so Daniel Berge, who's been working on diagrams recently, picked it back up and finished it off and did a really fantastic job. So there's even a nice little, you can give it a string with literal metafont syntax, or we also have a little sort of DSL where you can use Haskell combinators to build up these paths with constraints. So that's fun. That gives you a nice, it's a nice declarative way to talk about curved paths with some nice theory behind it that says, we can always solve this to find a path that meets these constraints and looks nice in some sense.
Rain, I could keep going with tech-related questions here.
Well, maybe let's switch gears for a moment and talk about Typeclassopedia.
Okay.
So, Typeclassopedia, for those of you who haven't seen it, is an encyclopedia of commonly used type classes in Haskell, functor, applicative monad, and such. And it's the place where I first really started to get a good grasp of what it is to be a monad No amount of burrito or spacesuit tutorials really did that for me. But looking at the actual laws that these structures satisfy and using them in practice is really where it started to click for me. So what would you say is, at what level is the Typeclassopedia targeted for? Are there prerequisites for Haskellers to come in and be able to use that information?
Yeah, I think certainly there are prerequisites, and I think it even says in the introduction. But I mean, pretty much the basics. You need to understand what types are, and understand about functions and currying and type classes and things like that. But so it assumes that you sort of understand the basics of Haskell, the language, but not that you know a lot about sort of the library ecosystem that's grown up around Haskell, right?
Right.
Although I guess some of the stuff that's in the Typeclassopedia is in fact in the Haskell standard, but even so, it still kind of feels like you wouldn't have to have that stuff. You could still have Haskell without the functor type class or whatever.
Right.
So yeah, it was. So I mean, it was a long time ago that I wrote it. At the time, I think I just saw a way that I could contribute. I mean, this is something I really enjoy, this sort of process of synthesizing a lot of information and then presenting it in a way that's accessible and engaging to people. So I saw this as a way that I could contribute. I thought I had a pretty good grasp on some of that stuff, so I decided to write. I mean, originally I published it in the Monad Reader, and I think I probably wrote half the article in the month before the deadline and half of it the night before. So I think everything about monads and arrows was all written the day before the deadline, but I think I then revised it some more after that. But anyway, yeah, and it's actually has been really surprising and gratifying, sort of how much traction it's gained in the community. I quite often get people coming up to me and saying, oh, thanks so much for the Typeclassopedia. That was really where I began to feel like I was, grokking some of this stuff, and so that's really cool. I'm really glad that it's been able to be that for people.
What about a mathematics background? So somebody who comes in and looks at this starts to see category theory and might get a bit freaked out. Is that required?
I don't think so. I mean, so I think in the Typeclassopedia I do, I make some comments saying, well, if you know category theory, this is XYZ, but I try to present it in a way that it makes it clear that it's not required. So I mean, and I think at the time I wrote it, I didn't even know very much category theory. I know more now. I still wouldn't say I know a lot, although everything is relative. So relative to most people in the world, I know a lot of category theory. But category theory is something that I love, and I really do get a lot of mileage out of it. But yeah, it's certainly, I think people come to the community and they see other people being really excited about it, and they misinterpret that as, this is something you have to know to learn this stuff. So yeah, it's.
So that actually brings up a question I wanted to ask you, which is, do you feel like developers need to know these abstract algebra and category theory concepts to be successful with Haskell?
I think to really be successful with Haskell, you certainly need to, at least you need to understand some of what's in the Typeclassopedia. I wouldn't say all, because there is some kind of esoteric stuff in there, but a good portion of it. And well, I don't know, is understanding the Typeclassopedia the same thing as understanding category theory or abstract algebra or whatever? I don't know. I would say maybe it is, but I don't think you need to understand category theory and abstract algebra in the way that people think that means. Like you have to go take a category theory class, because there's a lot of different approaches to these subjects and a lot of different sort of ways to present them.
And
So.
I've seen Haskell written with a wide variety of levels of abstraction, everything
Yeah.
from very imperative stuff that lives in an IO monad all the way through to Edward Kmet adding profunctors and con extensions.
Right. Right.
And it seems like people are able to get stuff done everywhere in that space.
Sure. Yep. I mean, I think, yeah, you know, to be able to sort of get the most mileage out of the existing library ecosystem, you have to understand the sorts of abstractions that are going to come up a lot. So you have to understand more than just the IO monad, but you don't have to understand con extensions. So, I don't know. But you can also get a lot done without without using a lot of the library ecosystem. So I don't think there's a right or wrong way to do that.
So what's the role for you personally in the Haskell you write today of some of these, higher order abstractions?
That's a good question. So, so certainly, within diagrams, we use some of these things quite a bit. There's lots of things in diagrams that are functors. There's lots of monoids. There's some applicative functors. Nothing in diagrams itself is a monad, but certainly in writing some of the backends, like the Cairo backend uses a rendering monad. Actually, most of the backends use monads. And then of course there's all sorts of crazy type system extensions that we make use of. And then in some of my research, which is not diagrams, but some of that really goes off the deep end. But in a sense, some of that it really should be written in Agda, but we're writing it in Haskell to be able to run it. So
it seems like there's a relatively short list of some of the most fruitful concepts. You mentioned monoids, functors, applicatives. A lot of those are covered in the Typeclassopedia, but maybe there's a need for an Algebraipedia for the uses of semigroups and monoids and some of those structures. And you cover a lot of that in the monoids prole, which is why I love it so much. But there are lots of those structures.
Sure. Yeah, that's a good. So beyond semigroups and monoids. You can talk about groups, but groups tend not to come up as much. I'm not sure I understand exactly why that is. Maybe part of it is that, a lot of things don't have inverses because you can't, inverses destroy information. And when you're computing, you often don't want to destroy information. So, so I don't know that I have a bunch of examples of a sort of richer space of algebraic things that are as useful, but there was an interesting paper at ICFP, or maybe it was the Haskell Symposium this past year, by Mario Blažević, I think is his name, where he has this whole hierarchy of basically factored monoid into a whole bunch of different sorts of things. And that's really interesting, and it'll be interesting to see if that how that plays out, if that turns out to be some more useful abstractions.
There's a Wikipedia page on variations of semigroups.
Yeah.
With a zero, with a cancellative element, various things. There are about 100 of them.
Right. Yeah.
And it seems like you could point to each one and then say, all right, what can we do in Haskell with this? And I've seen Russell Connor has a great blog post about the use of tropical star semi-rings.
Yeah, that's what I was just going to say. I realized just as you were saying that rings and variations on rings. There's a whole bunch of them, and I have seen some really cool applications of that. There's a series of blog posts by Ken Shan, I think, and I think he co-wrote them with someone else. I'll have to, I'll find it later and I'll send you the URL or something. But it was about solving this sort of problem where it was something like if you list out the first billion numbers in English spelled out in words, where is the 9,000th E, or something like that. And they solved in this really, really clever way by building this I think it was called a semi-near ring.
Yes.
And sort of interpreted it in different. So they built up this algebra and then interpreted it in different ways to get out information that they were interested in. And that was really, really clever.
Yeah, for me, I've gotten some of this from just talking to Edward Comet, and I say, "Hey, here's a structure. What do you do with it?" And he says, "Oh, well, you can do this and this and this."
Oh,
but
yeah, cool.
I don't have that mapping generally for that list of semi-group variations for ring-like structures.
Right.
There's probably a lot of cool stuff, and there's probably literature all over the math community for what what they're doing with them.
Yeah, exactly. Yep.
But I don't think
there's another paper in ICFP or the Haskell Symposium this year that I'm remembering that was about. I'm not going to be able to remember it now off the top of my head, but along similar lines, doing some really, really cool things with. I guess they were looking at some algorithms that come up in linear algebra, and noting that in fact you don't need a full vector space to do these algorithms over. You just need a semi-ring or something,
right,
or a ring or something like that, and you get interesting algorithms to fall out of it by instantiating it with different rings. So
there's a really interesting relationship that I'm just starting to discover between structures of various properties, strengths, and, for instance, languages of various strengths. What do you need to parse a regular language versus a context-free language, and so on.
Yeah.
It turns out that there are structures that map to those.
Right. Yeah, that's cool.
I don't think it's a coincidence that you wrote your paper on the monoid, because I see it everywhere I look now. It's hard for me to not see monoids.
Yeah, definitely.
If nothing else, you're working with a free monoid somewhere.
Right. Yeah, exactly.
And I used to think, as an imperative programmer, well, why do I need all this nonsense, right? I just want to get some stuff done. But what I'm learning is that the patterns that I had for imperative programming are so poorly specified and understood compared to the patterns you can get using these structures from math.
Yep.
So we're talking about mathematical abstractions. What about the role of other abstractions? I know that part of your teaching is teaching about abstractions. Do you think that abstractions from math just tend to be generally more useful, or should all computer science abstractions be rigorously defined in math, or are others useful? I know that some are a bit leaky, but exist in the sort of real world of engineering. What's your thoughts on those?
Let's see. It's a good question. I mean, I think that ultimately I see that the two often end up meeting in the middle, where you say, well, on the engineering or computer science side, we made some abstraction and it works. We can't really explain it, or we don't have a good formalism for it. But if you really dig deeper, you can find that there are nice ways to describe what was going on. And I think maybe the kinds of things that people tend to do, or that people tend to be able to wrap their heads around, are the things that have nice abstractions, nice mathematical abstractions at their core. So I'm not sure that there has to be a divide between the two, and I think, yeah.
Well, let's say I'm playing devil's advocate here and starting a religious war by talking about patterns, and there's all these patterns that have come up that really don't, at first glance, at least to me, seem like something from math. I'm having
Chris, we're going to
get. You're talking about like. Sorry, you're talking about like the Gang of Four book, those sorts of patterns.
Exactly.
Okay. Yeah.
We're going to get flamed so hard for this.
We're talking about it neutrally from a curious scientific perspective.
Okay, sounds good. So what's the question then?
So the question is that a lot of these patterns are kind of what seems like engineers have discovered from looking at their code or doing case studies and so on. And the way they're described is definitely not, in mathematical terms, at least not for the majority of them. Visitor and I don't know most of them, unfortunately, but
Right.
but they describe behavior more than a mathematical concept.
So I don't know a lot about patterns. But you just said visitor, and I think so. That's the one where okay. As I recall, my intuition is that visitor has something to do with like traversable or something like that. I mean, so in other words, I think there are mathematical abstractions that you can match up with these often. Just because they're not described in that way, it doesn't mean it can't be. And sometimes that's fruitful.
Yeah, so I guess this is a challenge to the listeners to come up with some abstractions that can't be formulated in terms of math.
Negative proofs are hard. I don't know.
Cale Gibbert has a quote that I love, which is only slightly trolling of imperative programmers, which is that design patterns are just libraries your language isn't expressive enough to write.
Right.
And one of the things I love about Haskell is that if you want a monad, you literally write a library.
Right.
It's a very small library that defines what a monad is, and then it's defined for you, and it's not an implicit understanding of a pattern. Right.
Yeah, and I mean, I think I believe that statement on some level, and I think another way of saying it is design patterns arise when your language doesn't have the right sorts of abstraction, right? Because we all know, don't repeat yourself, right? That's the mantra of programming often, and what a design pattern is exactly the sort of thing where you end up repeating this pattern. So you'd like to be able to abstract out the repetition, but if your language doesn't have the right mechanisms for abstraction, then you can't, and you need a pattern. And I think I'd have to think a while to figure out, to give a good example, but I'm sure these sorts of design patterns exist in Haskell too.
Right.
So I'm not trying to say, oh, Haskell, you don't need design patterns. Well, we do have them. They're just other things that Haskell doesn't let you abstract. So it'd be interesting to think about that and come up with a good example. But
so to get back to the visitor example specifically, a visitor is a way to separate the behavior you want to apply to members of some structure with the way that structure is organized. So it is very much a traversable or a foldable sort of pattern.
Yeah. Yeah, it sounds kind of like functor, but if you throw effects in there, then you need something like traversable to model it.
Right. But it's interesting when we talk about traversable, we can say, what are the types? That tells us a lot right there. What are any laws that it has to follow? Starting with the functor laws, that tells us a lot. It gives us a lot of stuff for free, actually.
Right.
And with visitor, while it's a useful pattern, all of that is implicit.
Yeah, it's very hard to reason about your code that you've written using the visitor pattern, where you don't.
It's better than code you've written without it.
Yeah, sure, but you have to kind of reason about it from scratch each time.
Right.
Yeah.
And it mostly my experience is that they provide a shared vocabulary more than they provide an explicit formalism for what you're doing.
Yeah.
It'd be interesting to think about, and probably not right now, but what you could do to make those things more formal in an imperative language. Is there much more room for that expressiveness?
Yeah, I don't know. I don't see why not. But yeah, I don't know.
So we've sort of wandered on to the topic of the craft of programming and elegance and readability and so on. And as I was reading your blog, I couldn't help but think that you remind me a lot of Donald Knuth, with this sort of obsession on beautiful code and beautiful presentation and so on. So how much did his work inspire your work?
Wow. Well, I'm quite honored to be compared to Donald Knuth. I'm not sure that it's merited, but you're right. We do certainly share that interest in beautiful presentation of things. Um, and yeah, certainly I think he's certainly influenced me. I don't think directly, but I think just in reading some of the stuff that he's written and saying, this is the way it ought to be done, and sort of being inspired by that. I haven't read a lot of the Art of Computer Programming. I've not read at all. I've read some shorter things that he's written, and I've read a few of the sort of pieces that he's been putting out of Volume 4, which has more to do with combinatorics, which is another thing that I'm really interested in.
I think if you claimed that you read most of the Art of Computer Programming, we'd have to call you out on that one.
Yeah, right, exactly.
So, sort of related to Haskell is do you think we're ever going to get past tech? I've seen some people, saying, look, it's a horrible language for programming in. We need something else, but there's so much momentum behind it.
Yeah, that's a really interesting question. I mean, to be honest, I think it's also a horrible language for typesetting things in. It's just really good at typesetting. It's just not much fun to use. So, yeah, I don't know. I've thought about that, but it's one of those things. We just need someone to come along who is as smart and full of hubris as Don Knuth, who can actually believe that they can make something better and then actually pull it off. And that combination is rare, I think.
And by the way, the smart there is very important. Hubris is not going to be
I know,
sufficient.
exactly. Right, because there's a lot of people who think they can make something better than tech, and a lot of people have tried and end up with half-working systems that are abandoned, So, yeah, I don't know. I don't know if we'll ever get something better. But yeah, knowing what we know now about programming language design, seems like there ought to be something a lot better. But obviously, typesetting is a really hard domain, and there's a lot of things that tech does right. So to replace it would be a ton of work, obviously. Yeah, and just of course, you mentioned the social work of sort of how do you replace this very, very entrenched software. I'm not, I don't know, and it would be tough.
Chris, would you like to move on to something completely different?
And now for something completely different.
Yeah, I'm really interested in what's new in Diagrams 1 and where you plan to go in the future.
Okay. Yep. So yeah, we released Diagrams 1 just a couple months ago, I think. We released it on the day I gave a talk at the New York Haskell users group, which the video I think was just finally posted. And so either today or tomorrow, I think we're going to actually post an official announcement of the 1.0 release.
So we are scooping it. I'm very excited.
Exactly. No, it's great. A lot of people know about it. It wasn't a secret, but we haven't posted a big announcement about it. But there's a lot of really exciting stuff. So one of the most exciting things I think is that we now have support for arrows. So you can have different things, in a diagram, and then say, I want you to draw an arrow between these things. And in fact, this was one of the original things. I wrote this original version in 2 weeks, and then kind of had to scrap it. One of the things was I wanted arrows, and I couldn't do it. I had sort of designed myself into a corner, and I couldn't make arrows fit.
So now we can finally draw commutativity diagrams.
Yes, you can.
Yeah. Let's be clear that we're talking about actual arrows you draw, not the other type of arrow.
Yeah. No. Right. Yeah. Exactly. So Jeff Rosenbluth is another diagrams developer who did most of the work on the arrows feature, and it's one of those things that's surprisingly tricky to do right. There's lots of, I think I said this in my talk at the New York Haskell users group. There's lots of ways for arrows to look wrong, and when they look right, you don't really notice them, and when they look wrong, you're like, well, that looks terrible, So, but yeah, that's really exciting. So we have that now. What are some of the other things? We have something Ryan Yates worked on, path offsets. So if you have a path, some kind of line through space, you can find another path that's sort of offset from it by a constant distance. So you can use that, I don't know, various artistic things you could use it for. You can also sort of use it to simulate stroking a path. So when you draw a path, you get some region with some width, and typically the back end kind of does that. But you can sort of do that internally now and get another path object that represents the stroked version and do something with that. What are some other things we have? So the metafont stuff that we mentioned earlier. We have a bunch more sort of tutorials. We have a nice little framework for making sort of command line driven programs for generating diagrams. So you can give it a function from, say, it takes an int and a color and it gives you a diagram, and that it automatically turns into a program that takes an int and a color on the command line and will generate that diagram. So that's nice. You could use that. Say you have some some data sets that you want to visualize, and you want to visualize them in some specific way. So you write a little program, a little function that takes in such a data set, maybe with some options, and outputs a diagram. And you can now really easily build a little command line thing that takes in the file name of the data set and a bunch of options as flags, and then outputs a diagram for you. So that's a nice little feature. There's probably some other things that I'm forgetting, but yeah, that's some of the new stuff that's in 1.0. Some places where we're heading with it. Let me think. What are some of the? So a larger project I've been working on with. So Diagrams currently does have some support for animations. You can build up these active values. It's an applicative functor, and so you can use all the applicative machinery to build animations. But in a sense, it was sort of always, well, I won't say a hack, but I didn't quite understand the semantics of it very well. And so together with Andy Gill and Nick Wu, we've been sort of working on a complete rewrite of this active thing based on a much cleaner semantics. And it's actually based on two categories, if you must know, but you don't need to know that to use the library, right? So I really think that'll work out nicely. And then at the same time, some of the people are working on some much nicer support within some of the Diagrams backends for generating animations. So like right now, if you make an animation, the only thing you can do is output a directory full of images as frames. And then you have to put them together into an animation yourself. And I think Jeff Rosenbluth has been working together with Vincent, I forget his last name, but he's the author of the Juicy Pixels library. They've been putting together something that will let you sort of directly generate like an animated GIF or something like that without ever writing the intermediate files to disk. So that'll be fun. I think people will have a lot of fun building little animations using diagrams.
So how much does this work with animations intersect with Connell Elliott's work with functional reactive programming and his, I think it was Pan, I'm thinking of?
Yeah. Yep. So it certainly does intersect, and the big unifying thread is thinking of animations as functions from time to diagrams. That's sort of the underlying semantics. One of the biggest differences is that all the work on, like this work I was talking about with Andy Gill and Nick Wu, we don't have reactivity in the picture at all. So it's just building a static animation, if you will. So, of course, that simplifies a lot of things. But there's still a lot of interesting questions there. So we've sort of taken a simpler piece of the design space and tried to really understand that well. But there certainly is a lot of relationship there. And also some of Paul Hudak's work on polymorphic temporal media, there's a lot of relationship there too.
So I see. I've seen this start to get used for data set visualizations, and I think as interest grows in, data science or whatever we want to call it now, there's a lot of interest in D3 and so on. Are you thinking that you can tackle that space, or is that something you're interested in long term?
Yeah, I think so. So I'm not that familiar with D3. I mean, I've seen a lot of what it can do. It's really impressive. I've never written any D3 code myself. So, data visualization is not, it's not what I'm personally interested in. So that's not sort of why I develop diagrams. I think that building a data visualization library or toolkit on top of diagrams could work really well. And there have been a few people that have sort of talked about maybe doing something like that. What we do have right now is that the Haskell chart library. Jan Bracker did his a Google Summer of Code project on porting it to use diagrams as a backend. So chart, it can make like a few certain types of charts. And now that it uses diagrams as a backend, that means that you can then anything that diagrams has a backend for, you can use with charts. But it's not sort of a general purpose data visualization toolkit, right? And so that's what I'm hoping that someone will build on top of diagrams. It won't be me, but I think it would work really well for that.
Raina, I assume we're both kind of running dry on questions here, but
Oh, I have a question. So I noticed that you started writing a guide for the Catster episodes on YouTube,
right.
and I have just been watching those as well. So I'm excited that you.
Great.
I'm going to go read that now.
Great.
So it seems like there's a lot of opportunity now for some really good education on both cat theory and abstract algebra to make it available to people who are not in a math program at a university.
Yeah.
And A-Woody has some category theory lectures on video on YouTube. Those are great.
Yeah.
But I want more. Where can I get more? Who's gonna put this out there?
I don't know. That's a good question. I really hope that I get a chance at some point to teach a course on sort of the intersection of category theory and functional programming.
That's exactly what I want. Exactly.
Yeah. So Mikhail, what's his last name? I don't know how to pronounce it. Vedemo Johansson. He taught a course like this a while ago, and he had some lecture notes from that. I'm not sure what happened to that. I think he was maybe thinking of turning it into, something a little more like some kind of book or something. I'm not sure where that went. But that was exactly that. He sort of used Haskell as a vehicle for teaching category theory to his students. I think this was at Stanford or something like that.
And are those lecture notes available outside of the class?
They used to be. I don't know if they still are.
Well, so I might ask you about that after this, because if I can include that for people. My issue is I don't have an academic background, so the world of lectures and things like that is still a walled garden for me. And so every now and then someone will say, well, here's a link to some random professor's page, and here's a bunch of stuff that they have, and now it's like I've unlocked a treasure chest, right? But it's very
exactly. Yep. I think Graham Hutton has some nice category theory lecture notes too. I know those are available, but
So maybe what I'll do is I'll get all of the stuff that you can think of and make a big list for the people who
sure.
are watching this and for myself. And
Yeah, sure.
I'd love to have a big, wiki or some place to say, hey, here's all the stuff that people have made available.
Yep.
Maybe I'll just start doing that.
Sounds great.
So we almost missed the chance to ask you about what it's like teaching an introduction to Haskell class. I assume the
sure.
students are rather kind of self-selected if they're picking something with Haskell in the title.
Yeah, they are. That's true. So I taught the course 3 times. So this was a sort of half credit course. So I met once a week for like an hour and a half at the University of Pennsylvania. And yeah, it was a lot of fun, and that certainly has shaped the way that I think about teaching and about Haskell. And, as you said, it was certainly self-selecting. So I think it's very different than teaching like an introductory course to college freshmen, or like a required intro course using Haskell. That would be a very different experience. But at the same time, I mean, the students that would take it, a lot of them didn't know any Haskell at all. They were just interested. They kind of heard about it or whatever. So, but yeah, a lot of them picked it up really well. I'm trying to think sort of if there are any sort of bigger lessons that I.
Was there a consistent hurdle that they had difficulty getting over?
Yeah. So I think so one interesting hurdle that I came across that I think I did a better job the third time I taught it is that students were doing really well right up until about we hit applicative functors. And then they started getting really confused. And I think, and then we did monads, but they were just very confused. And I don't think any of it clicked very well enough for, some of them, the best students, they got it and they, were able to go on. But maybe you could say, well, you just went through it too fast. And maybe that's true. But I think a big thing that I realized, and I think I had a blog post about this a while ago, is that when you're thinking about, any of these things like functor, applicative, monad, right? They define an interface, and there's actually 2 different activities that you can talk about. You can talk about implementing an instance. So say, well, okay, implement the monad instance for the function arrow, and then there's programming on top of the interface, sort of using the monad abstraction to write programs. Those are 2 very different activities, and I think I didn't do a good enough job separating those, and students got really confused. They would mix the levels up, right? They were trying. I was asking them to program against the interface, and they were thinking about the implementation, or vice versa. And I don't know. I think so. There's a larger issue here of a lot of computer science and math really is all about this sort of moving up and down between different levels of abstraction, and being a good programmer, being a good mathematician is a lot about training yourself to be able to move between these different levels of abstraction and not get them mixed up, and sort of be able to switch in your head. And I think that's something we need to explicitly teach students. Maybe right now it's like, well, the students that are already inclined to do that anyway get it, and the students that don't understand that get confused. But maybe there's a way that we can explicitly teach moving between levels of abstraction. So I don't know. I haven't figured that all out, but it was interesting. So the third time I taught the course, I split applicative into 2 classes, and the one I just focused on implementing it, and the other I just focused on, okay, let's forget about any specific instances. What can we do with this interface in general? And I think that worked a lot better, separating it like that. So.
Okay.
So what do you think about Haskell as a general purpose language for teaching functional program, or for teaching programming, for teaching computer science? I know University of Texas at Austin used to use Haskell, I think, in the 90s, and I think I even remember Dijkstra saying, hey, no, we can't use Java, we have to keep using Haskell, it's better. And then he left, and then they switched.
Yeah, exactly. Yeah, that's an interesting question. I don't know. As much as I love Haskell, I don't know. I kind of go back and forth on this. So actually, here at Penn, we now teach our intro course, the first half in OCaml and the second half in Java. And I think the PL people here would love to teach the whole course in OCaml, but sort of for pragmatic reasons, a lot of the downstream courses say, well, they have to know Java, so well, that's fine. But but the reason, so why did they choose OCaml and not Haskell? I think one of the biggest hang-ups is that you can't. It's very hard to reason about time and space usage in Haskell, and that's traditionally a big part of an introductory education in computer science. And until we really understand how to do that in Haskell, it's just really hard to, you just have to say, well, we're going to learn this language, and well, don't worry if your program's not efficient. You will learn that in your third year. I mean, that's kind of doesn't cut it. And I don't know, and I think there's also there's just a lot of abstraction and a lot of details to get through to understand the language, to work in it. That's something I definitely ran up against teaching my intro course. Just figuring out how to sequence all of the introductory things, and how to make sure that well, I can't talk about this yet because I haven't talked about this, and figuring out a good order and sort of. It just felt like there was more and more and more stuff that I had to cover that I was taking for granted. So, for that reason, it seems like it might not be the best as an introductory language. That you might want something with a little bit simpler syntax, maybe with not so many features, or maybe even a dialect of Haskell that was simpler. So I know there used to be this Helium project. That had sort of like language levels for Haskell, where you had, and I think that could be really, really great. But that's a lot of engineering work to make something like that happen, which is why Helium was sort of an academic exercise, and then no one's maintaining it now. So
I don't know if it's industry pressure as well. We're sort of creating a self-fulfilling prophecy that you train people in Java so they can enter the Java workforce.
Right. Yeah.
I remember when SICP moved from Scheme to Python, and I died a little bit inside.
Yeah, me too. I don't know.
So you have a little bit of experience, much more than most people with teaching beginners and introductory level Haskell. My experience has been that Haskell doesn't have a very good story for beginners, that it requires a lot of self-direction. And even things like the Typeclassopedia, which are great resources, you have to know that it exists. You have to go find it.
Sure. Yeah, definitely.
Are we missing? Do we need better books? Like, what kind of resources would help fix this problem?
Yeah, that's a good question. Yeah, better books, better. Maybe it doesn't even have to be books. It could be some kind of interactive website with videos, and you get to type in a box, and it. I don't know, but.
For me, School of Haskell has been the best resource I've found.
Yeah.
And I hope people go out and write a bunch of School of Haskell tutorials.
Yeah, I mean, School of Haskell is definitely heading in a cool direction. I mean, unfortunately, that's not getting beginners to learn programming with Haskell is not at all FP Complete's goal.
Right.
And so I don't see them putting a lot more effort into developing School of Haskell in that direction. But I think taking some of the ideas from that Yeah, it could work well. I mean, the problem, of course, is that all of this takes a lot of time to develop, and it's not just about the technology. Developing the material and figuring out how to order things and how to explain things in good ways. It's really tough, and it takes a lot of time. And someone just needs to come along that they really have a passion for that and put the time and effort into it.
So before we wrap up, Brent, what would you like to talk about or introduce to the listeners that we haven't covered yet?
Oh,
or is anything
no.
on the horizon for you? Are you just continuing along the path with diagrams? And I mean, are we going to see anything? Do we get a sneak peek into anything that you're working on?
So my dissertation research is all about the theory of combinatorial species and how it relates to functional programming.
And you actually just finished a paper, didn't you?
I did, yeah. So along with Jacques Corrette and my advisor Stephanie Weyrich, we just submitted a paper to MSFP, Mathematically Structured Functional Programming. That's about this sort of taking combinatorial species as a foundation for data types, or for certain kinds of data types.
Could you give us a quick intro to combinatorial species? No,
but I can tell you sort of why they're interesting or what the point is.
Sure.
I won't tell you any definitions, but you can read my paper for that. But so I mean, combinatorial species are a very general framework for describing structures, right? I mean, much like algebraic data types are a generic framework for describing certain kinds of structures, right? And combinatorial species are much more general than that. But the sort of big innovation, it was an innovation at the time in combinatorics, and I think this is kind of what our paper is about. I think this could be a cool innovation in the space of describing data structures as well, is that combinatorial species or structures built with combinatorial species are explicitly labeled. So you have sort of positions in these shapes that can hold data, but those positions have labels, and you can actually manipulate the labels in certain ways. And part of the reason this was interesting in combinatorics is that it gave a kind of for the first time a really concrete way to talk about so-called unlabeled structures. Everyone thought they knew what was meant by unlabeled structures, but it turns out really to talk about them rigorously, you have to talk about sort of equivalence classes of labeled structures under certain relabelings. And so the idea is that thinking of data structures in programming as being these labeled shapes filled with data will let us, unify a bunch of different things. So like you can talk about algebraic data types, and you can also talk about arrays, and they both fit really nicely into this framework. There's other things you can do with it. I mean, in a sense, we're just kind of starting to explore this. So yeah, I mean, I think I'll be making a copy of that available pretty soon, and there'll be more to come. So, I had this library called Species. It's on Hackage. I doubt it compiles anymore. But that was really just about sort of computing with the mathematical abstraction of species. But we have a whole bunch of Haskell code right now. It's not in any kind of state to be released as a library, but I think there could be some really cool libraries coming out of this that would let you work with data structures in some cool generic ways that are maybe not possible or not easy to do at the moment. So.
Okay, well, we're about out of time, but I wanted to thank you, Brent Yorgey, for joining us on the Haskell Cast talking about diagrams. Thanks for the Typeclassopedia. I think I say thank you on behalf of a lot of people for writing that. You've been listening to the Haskell Cast, Episode 5, recorded on January 17th, 2014. For links and information about the episode, go to www.haskellcast.com.